Hello everyone, in this video we will see about inverse kinematics. Okay, so first we know that what is inverse kinematics. So task space will be known and we have to find the joint space. Okay, so that is you could see in the picture. So forward kinematics is your joint space coordinates are given where we have to find the task space, that is a Cartesian space, and in inverse kinematics that is vice versa of this. So that is task space is given and we have to find these joint space coordinates. Okay, so that is from moving from task space to joint space is like going from a desired position and orientation of a robot's hand to figuring out how each joint of the robot's arm needs to move to get there. Okay, so it's all about finding the right combinations of joint settings to achieve the specific location and orientation you want for the robot's end tool. Okay, considering where it starts from. So next is about a manipulator workspace. So you know that you have reachable workspace and dexterous workspace. So we will see what is a reachable and dexterous workspace. Imagine a robot's hand and the area it can touch. Okay, the reachable workspace is like the space the hand can reach with at least one way to move. It's not great for doing intricate tasks. Okay, now think of the dexterous space as the area the hand can reach, but this time it can handle things from any angle. It's like a subset or the same as the reachable workspace, but it's more versatile and useful for tasks because it can grip and work with objects from all sides. Next, we have seen the forward kinematics of 2 degree of freedom RR planar manipulator by using geometric approach, and we have found the position and orientation of the end effector. Now inverse kinematics of this the same by using geometric approach. Okay, so consider the same RR manipulator. Here we have two links and here it is named as A1, A2, Q1 and Q2, which are the thing we have to find. Okay, so we know the task space coordinates as x and y, the position and orientation are known. Okay, but we have to find the link and the joint angles. Okay, so for this first what we have to do is how can we by geometric approach or by inspection method, how do we find these joint angles. Okay, joint angles and the link variables. Okay, so first by applying Pythagoras for this robot, that is for these links, and here I have named this as x, y and r. Okay, along x-axis it is x and along y-axis it is y, and the orthogonal is r. Okay, so by applying Pythagoras, so we know that r square will be equal to x square plus y square. And next, now considering only the upper part, considering only one link. Okay, so in this I'm considering the angle as reverse angle as alpha. So applying cosine rule for this, you will get here r square is a1 square plus a2 square minus 2a1 a2 cos alpha. Okay, next from this we can able to find the cos alpha as a1 square plus a2 square minus r square by 2a1 a2. Okay, so here r square we have already found it as x square plus y square, so here replacing that, so you will get as a1 square plus a2 square minus x square minus y square by 2a1 a2. Okay, so from this we have to find, we know that what is q2 angle. So q2 is 180 minus alpha, that is here pi minus alpha. So alpha here this can be written as just apply cos, that is pi minus alpha, that is 180 minus alpha can be taken as minus cos alpha. Okay, so applying cos on both sides as cos q2, which will be equal to minus cos alpha. So we know what is cos alpha, we have found what is cos alpha, so cos q2 is equal to cos alpha. Okay, so we are applying negative sign here, so you will get as x square plus y square minus a1 square minus a2 square by 2a1 a2. Okay, next the considering the second link. Okay, so here you are going to apply simple trigonometry. Why? Because here we are doing this inverse kinematics by inspection method, that is geometric approach. So you are considering the second link. Okay, so here after applying a simple trigonometry, you will get here as sin q2 is root of 1 minus cos q2 square. Okay, so now considering the whole considering both links L1 and L2, that is here as A1 and A2, again simplifying this, we will get, and considering the angle as beta, everything by assumption, okay, by inspection. So beta as tan inverse of A2 sin q2 by A1 plus A2 cos q2. Okay, so now considering the whole, whatever we have considered as the earlier one, as in along x-axis we have considered this as x, the triangle as x, and along y-axis it is y, and along the Pythagoras theorem we have considered this as r, right? The whole triangle we have partly solved link 1 and link 2, and then now we are coming back to the whole triangle to solve. So we have considered here we are going to assume as angle gamma. Okay, so here gamma is tan inverse of y by x. Okay, and here q1 is, so we have to find the q1 angle. Okay, so that is gamma minus beta. So we know what is beta here from the previous diagram, we have got what is beta, and gamma is now only we have found as tan inverse of y by x. So substitute in this, we will get the q1. Okay, next, now what we have got, what is q1 and q2, the angles. Okay, by using the links a1 and a2. Now the other approach or other method is, if the link is twisted in this, you will get as q2. If the link 2 is, that is a2 is twisted on the other side, you will get other solution, right? So we are going to see second approach as, this can your this is by geometric method or by inspection method, right? So the link 2 can be moved whichever side. Okay, so now the second method, if you are considering this way, the q2 will be, previously we have got cos inverse of x square plus y square. Now you are giving us negative sign if this is twisted in this way. Okay, and again the same example, considering the same assuming the same angles, you will get q1 as, previously we have got tan inverse of y by x minus tan inverse of a2 sin q2 by a1 plus a2 cos q2. Here you will have the positive side. Okay, the sign change will be there if you are considering the opposite side. So here q2 and q1 for this, if the link is twisted on the other side. Okay, so you could see here the two solutions of the same 2 degree of freedom RR planar robot. Okay, so we have solved only the first method. Second method, you will have the change of sign if it is twisted on the other side. Okay, so we have seen this by geometric approach, the same thing we have seen, okay, in forward kinematics as position and orientation of the end effector. How will you prove this, whether the solution whatever we have got in the inverse kinematics is right or not? Okay, for finding that, just for this forward kinematic model, you just apply these trigonometric identities. Okay, so cos a plus b is can be taken as cos A cos B minus sin A sin B, and sin A plus B is sin A cos B plus sin cos A sin B. Okay, so apply in this position of the end effector for this forward kinematic model, and okay, squaring on both sides and adding two equation. Okay, you will get cos theta 2, which will be similar to your cos q2. Okay, this is how you can verify the solutions by using this uh, forward kinematic model. Okay, the inverse kinematic model can be verified by using the forward kinematic model by applying simple trigonometric identities. Okay, so here cos theta 2 is similar to what you have got as cos q2. Okay, next. So here we have assumed some angles as alpha and beta, right? So that also can be found. Here tan alpha is taken as L2 sin theta 2 by L2 cos theta 2 plus L1, and tan beta is y by x. That is what we have seen as tan inverse of y by x, right? The beta and alpha we have found by using inverse kinematics, right? The same thing you can verify by having this forward kinematic model. You can apply the simple trigonometric and you can verify the forward as well as inverse kinematics. Inverse kinematic solution can be verified by using the forward kinematic model, okay, by applying simple trigonometric identities. Okay. So next, what are the issues in inverse kinematics is, so figuring out the way a robot's joint should move to reach a specific point is not easy. Okay, it's like trying to solve a complex puzzle and the solution is unique for each robot arm. So the math involved challenging. So we are dealing with tricky equations involving things like sine and cosine, which can get pretty complicated. Often there are some more equations than unknowns, and they are interconnected in complex ways. Okay, so this can result in multiple solutions. In some cases, or sometimes there is no solution at all. So for a robot to reach a particular spot, that spot must not only be within its reach, but also in the most versatile part of its reach where it can handle things from all angles. Okay, so this is all about inverse kinematics. Thank you.